Yeah, unfortunately, if we press the buttons on the screen, then all kinds of things I don't understand happen. There are many functions in this camera. I only understand the three I use. But you can edit. I don't even know what you can do. I will begin. Dear Heavenly Father, we thank you for today. Again, Lord, I thank you for these students. Just ask you to bless this class. Help us to glorify you, Lord, and we do this day, Lord. In your name I pray. Amen. All right, so onward. Multivariate functions and limits. So I've already started talking about multivariate functions because, you know, I think you guys actually understand them sort of intuitively. But the limits for multivariate functions, well, that's a little bit new. So in my notes, I have some short discussion of what's known as, sorry, eventually find my way over to my notes. You know, I missed 20 minutes between classes. We used to have 20 minutes between classes. It was helpful. So I have a discussion of basic Euclidean topology at the start of this chapter. And I think it'd be healthy for you to read it. I'll use that terminology from time to time. Basically, there I describe what we mean by a set being open, what we mean by a boundary point, and then ultimately what kind of points we're allowed to take limits at. So, you know, maybe I'll come back to that later. I don't feel led to talk more about that today. But ultimately, that leads us to what's called a limit point. And here's the definition. We say a limit point, a point's a limit point if every open ball centered at y contains points in d minus y. So if I've got some kind of set, D, right, and if I pick a point, like say here, y, then what's an open ball? Well, for this two-dimensional thing, open balls are just open disks, something like that. So it's a limit point if no matter what open disk you look at, there's points inside D. In that case, this case would be these, then that would be a limit point. Now the other kind of point you could have would be something like out here, an isolated point, right? And so an isolated point, if you look at open balls around an isolated point, well, if they're too small, you see that there's no points in D. So that's called an isolated point. So this point out here, let's say Z naught would be an isolated point. Depending on what book you read, sometimes they'll define limits at isolated points just by kind of default. They'll say the limit at an isolated point is just the value of the function at that point, provided it's in the domain or something. But really, the kind of limits we're most interested happen at these sort of more interesting limit points, where either the point is on the edge of the shape we're considering, or it's perhaps inside. If it's inside, then, you know, as long as you don't take too big a ball, all the points in that neighborhood of your given point P are inside the set you're considering. And that's what we mean by limit point. So a limit point is, it's some point in the set which we can approach the point from lots and lots and lots of different directions, all right? It could be that you're on the edge of things, so maybe you can't approach from like outside the set or something. We'd still like to talk about limits in that case. But honestly, most of the examples that I'll talk to you about really fit more into this picture. And so we want to describe what on earth we mean when we say something like the limit as P goes to, say, some point P naught. Well, let's say X, rather. Better yet, let's say vector R goes to the point P. I'll say vector R goes to vector P of f of R. You know, what would we mean this equals to L? What does that mean? I will give you the careful definition, and then I will walk away from it, okay? But just for the sake of completeness, let me just state the careful definition for you. Get it out of my system so we can go on here. Definition. if f, oh, this definition is even more general than I want. Curses. I'm going to dumb this down a bit. If f is a function from some domain which is a subset of, say, Rn to R, so we're talking about a real valued function of n variables, has limit point, let's say R naught, then we write the limit as R goes to R naught of f of R equals to L. All right, if for each epsilon greater than 0, there exists delta greater than 0, such that 0 less than the length of R minus R naught less than delta implies that the absolute value of f of R minus L is less than epsilon. So this is the definition for the limit of a real valued function of several variables existing at a point. Now, I'm assuming really that the limit point is, well, I mean, actually, if you sort through it, this definition would still make sense for an isolated point, and that's kind of the funny thing. Anyway, let me stop making Math 200 type comments in here for a second. I mean, this is the definition. What does it say geometrically? This geometrically says that the limit exists, right, at the point if the values of the function can be made arbitrarily close to the limiting value, provided you feed it inputs which are sufficiently close to the limiting point. This is exactly the epsilon delta definition that we gave in Calculus 1, but how many people here did not have an epsilon delta limit in Calculus 1? Show of hands. So about half of you, right? So I cannot in good conscience cover this in here in reality. I mean, like, it's not fair to you guys because there's always transfer and other things, so we can't really stick to this here. And so I'm stating it for the sake of completeness. I want you to realize if you're from here and you saw this in Calculus 1, the same stupid definition still makes sense. All I had to do, what's the difference? I replaced, in Calculus 1, this was just absolute value of x minus x naught, right? But otherwise, this definition is the same, right? And that was what we needed to say the limit as x goes to x naught of f of x equals to L. So like that epsilon delta definition for the limit in Calculus 1 still makes sense here, provided that you replace the absolute value with the length of a vector. All right, now that I got that out of my system, let me talk to you about how to actually calculate limits in Calculus 3. So what's the trouble? So here's the main point. If we had the limit as x approaches a, right, or let me say x naught from the right of f of x equals to L, and we had the limit as x approaches x naught from the left of f of x equals to L, what did we get to conclude in Calculus 1? Everybody should have seen this. Yeah, the double-sided limit exists, right? Left and right limits both existing. That's plenty of data for us to get that the double-sided limit exists and is equal, right? In fact, if the left and right limits do not agree, right? If we had L1 and L2 and L1 is not equal to L2, or L plus and L minus and L plus is not equal to L minus, then of course the double-sided limit did not exist. Jump discontinuity, right? Okay, great. So now let's up the ante. Let's think about functions of two variables, right? We can still visualize. We can visualize these, right? So visualize with a graph. Z equals to f of xy, right? For xy in the domain of f. So let me do one I can actually graph. How about this one? So this would be z equals to what? You're like, well, your picture's not to scale, or, I mean, there's infinitely many answers. Which one do you want, right? Oh, there you go. X squared plus y squared will do it. So this is really the graph of the function x squared plus y squared, right? What's the domain? What's the sort of natural greedy domain for this? For what x and y does x squared plus y squared make sense? Right, the domain is naturally taken to be R2. There's no limitations here. So you can easily calculate things like, what's the limit as xy goes to, let's say, 3, 4 of x squared plus y squared? What would that be equal to? Yeah, 25. It's 3 squared plus 4 squared. So what Nathaniel just did was to plug the point in and basically observe, well, you can do that, right? I mean, that's the sort of the most basic thing is, if the expression you're looking at doesn't have any trouble at the limit point, what do? You just plug it in. That's still true here. What gets subtle is, if you think about what does it take for the limit to exist, right? If I could, well, I'm going to have to look at a different point, but the only point I can really visualize worth anything is maybe, say, this one. I don't know. That's actually not the greatest point, but that would be over, say, 1, 0, right? And so if we look at this point 1, 0, you can look at different paths approaching that point in the xy plane, right? Look at different paths approaching that point, and those will lead to different curves along the surface, right? But they're all converging to that same point on the graph, right? No matter what point I go through, I mean, no matter what path. So if I take a path, right, r of t, let's see here how to say this. If I take a path through, words, a path through 1, 0, right? And let's say that's, you know, t maps to r of t. Then what? And let's say that the path goes through this at time what? Let's say time 0, just for the sake of discussion. Then you can tell me what's going to happen. If you look at, you know, f of r of t, what happens to that? That's going to go to f of r of 0, which I'm assuming is what? F of 1, 0, right? It's going to be equal to 1. It doesn't matter what path I pick, right? All the infinitely many different paths I can approach the point 1, 0 through, they're all going to correspond to, you know, curves on the graph. What's the actual parameterization of this spider webby thing I looked at up here? Here you're actually looking at the path t maps to. So the first two coordinates would be given by r of t. What's the third coordinate, though? F of r of t, if you want to maybe be more geometric. I mean, it's a curve in 3 dimensions. I'm just saying I'm picking the first 2 dimensions to be the path and the domain, and then the graph says that the z is related to the x and y according to f. There's lots and lots and lots of different paths. No matter which way I approach 1, 0 down here, there's no jump in this graph, right? The graph is continuous. So all of those different paths all lead to 1. So here's the thought. If we consider paths, t maps to R1 of t, and t maps to, say, R2 of t, where R1 of 0 equals to R2 of 0 equals to the point in consideration p, right? So suppose we have two paths through the limit point p, right? And on the one hand, we have that f of R1 of t, right, goes to L1 as t goes to 0. And 2, we have f of R2 of t goes to L2 as t goes to 0, right? If you could find paths R1 and R2 through the limit point such that when you evaluate the function in question, you get limit L1 and you get limit L2 on these two different paths, if they don't agree, then what? Can the limit exist? No. I mean, if you sort through this definition over here, you can feed like a path through the function, and it should satisfy this business over here, no matter what path you're looking at. I mean, this you can picture R naught, right? And you can take any path through R naught, and that should imply that the image is within epsilon units of L. So if you can find two paths which violate this limiting procedure, it follows that the limit doesn't exist. Anyway, so this is so punchline. If L1 is not equal to L2, then the limit as R goes to P of f f of R does not exist. All right? So this is the so-called two-path no-go theorem. If two paths disagree, you're out of luck. All right? Right. This is if at least the failure if left and right limits don't match. If we can find two different path limits. The thing is, if you think about path limits in the one-dimensional sense, there's only two paths to go on. Path from the left, path from the right. I mean, that's the only way too. But if we think about a two or higher dimensional limit, we can approach that limiting point from many, many different paths. Here's this I cannot draw the picture for. All right. So let's consider the limit as x, y. It'd still be three-dimensional. It's just I just can't draw it. So if you guys were, let's see here. How about x over x plus y? Right. I'm very bad at making examples up. I fortunately cut out some pages from Rogowski, so I'll have some more problems to work after this one. Hopefully. Oh, he's got all the fun problems in here. Where's the... By fun, I mean differentiation, which is, really what I'm after. Oh, here's some token problems. All right, anyway. So, first of all, this is not like example 1. Can we just plug in the limiting point? No, no can do. Because if you do, you get 0 over 0, right? Which is indeterminate. So what we can do is consider path limits. So consider path, how about this? We can consider the path t comma 0 maps to 0, 0, aka x equals to t, y equals to 0, right? So if we go look at the limit of t comma 0 maps to 0, 0 of x over x plus y, what's that equal to? In other words, the limit as t goes to 0 of what? I plug in x equals to t, right? X equals to t, y equals to 0. We get the limit, the t's cancel. So the answer is 1. But if we look at the other path, right? What happens to the other path? So we get 0 over 0 plus t, right? Now this is not ambiguous. This is not indeterminate. This is just straight up 0. Because in this limit, we consider t approaching 0 but not equal to 0, right? That's the whole point of the limiting process, is you get arbitrarily close to the limiting point, but you don't actually get there, right? So this is just straight up 0, a la calculus 1 logic. And so that's 0. 0 not being equal to 1, we have shown that this limit does not exist. By the two paths disagree. So thus, the limit as xy goes to 0, 0 of x over x plus y does not exist. And of course, when I say does not exist, I mean does not exist as a real number. If you're a more philosophical type, you could seem like we just had this long discussion about this thing. How is it that it doesn't exist, but we just talked about it for 10 minutes? It's kind of weird. Right? So when we say something does not exist, we're talking about it as a real number, not as a mathematical construct. Just saying. All right, let's see if I can find another example here which is trickier. How about number 12? Which, oh, by the way, guys, I will, of course, post these for you as soon as I get a chance to scan them. All right? Here's number 12 from the review session I have not yet posted. So we got the limit as xy goes to 0, 0 of x cubed y squared plus x squared y cubed divided by x to the 4th plus y to the 4th. We're supposed to either evaluate the limit or state that it does not exist. So I use the coordinate paths. I mean, if you really look at what I did in this last example, what did I do? I mean, if you look at it, basically I exploited this path, right, and this path. And we saw that those two different paths disagree, right? Will that work here? What if I try the coordinate paths? Is that going to work? Terrible algebra. Let's see here. Well, there's an x and a y in every term upstairs, right? So if I look at the coordinate paths, I'm going to have 0 for both coordinate paths, if you think through it, right? Maybe we should try, instead of the coordinate paths, let's try something a little bit more adventurous. Let's try an arbitrary path. Let's consider x equals to t and y equals to mt for, arbitrary m. So in other words, what I'm suggesting is instead of just doing, an arbitrary specific path, let's just pick on any old line, slope m. Because why not just do it for arbitrary m? If we sort through this and we get a formula which depends on m non-trivially, we just take two different values of m and then we've proved the limit doesn't exist. Right? Let's try it out. So the limit of t, mt, goes to 0, 0 of that thing, x cubed y squared plus x squared y cubed divided by x to the fourth plus y to the fourth. So what do? We're going to set x equal to t, right? So what's that give us? That gives us like a limit as t goes to 0, right? And what do I get? T cubed, right? Times mt quantity squared. And over here I get plus what? T squared mt quantity cubed, right? Divided by what? T to the fourth plus mt to the what? To the fourth. This looks promising. This looks promising. See, because what do I got? I have a t to the fifth upstairs, right? And what do I have downstairs? T to the fourth. Bummer. So this is m squared plus m cubed t to the fifth, right? Divided by what? 1 plus m to the fourth t to the fourth. This is very, very disappointing, because this gives us m squared plus m cubed divided by 1 plus m to the fourth limit as t goes to 0 of t. Right? What is that? That's 0, yeah. Oh, well, great. So what have we just proved? We've proved that the limit, the path limit, corresponding to this multivariate limit, it's 0 for any possible linear path through the origin. That must mean the limit's 0, right? I mean, it seems intuitive. I mean, it's true that this path limit's equal to 0. It does not imply, though, unfortunately, that the original limit's 0. There are examples which conspire to have all linear paths agreeing, but when you look at quadratic paths, they disagree. So maybe this is such an example, yeah? How would we look at quadratic paths? So what I'm trying to tell you is that it's a great no-go theorem. If we can find two paths that disagree, we're good. But if we find two paths, if we find an infinite family of paths that agree, it's still not enough to prove that it exists. At this point, you might go, is there any hope we can ever show one of these things exists? Well, yeah, there's ones like this without indeterminate points, right? There's other problems that are squeeze theorem. You can still do squeeze theorem stuff. Let's try parabolic paths on this. Maybe that'll crack it. So how would we try a parabolic path on this one? How about we set x equals to t, y equals to, say, kt squared, right? Then when we look at the limit, we'll look at the limit of, t, comma, kt squared goes to 0, 0 of this, x cubed y squared plus x squared y cubed divided by x to the fourth plus y to the fourth, yeah? So we got limit as t goes to 0 of what? Is that any help? Am I still wasting our time? So this gives us we got ourselves a t cubed, kt squared, rather, plus t squared, kt squared cubed, divided by t to the fourth plus kt squared to the fourth. Now I got to sort through those laws of exponents. What do we got? The first term has got what? T to the k squared, t to the seventh. What's this one? K cubed, t to the, t to the eighth? T to the eighth. Down here, what do we got? We got ourselves a t to the fourth plus k to the fourth, t to the eighth. So how do we make this behave? Factor? Okay. I'll allow it. So what should we factor out of the numerator versus the numerator factors out a, what, t to the seventh times k squared plus k cubed t. Denominator, we can factor out a t to the fourth times 1 plus k to the fourth, t what? T to the fourth, yeah? Got bad news, folks. After we cancel, we've got a residual t cubed. It still works out to 0. I'm starting to wonder. Maybe this one actually is converging.
Wait. Was there a reason why the switch from limit to 0 to infinity?
Oh. Curious. No good reason. I mean, there's often a relationship between 0 and infinity, but that's not it. Anyway, the point is that this is 0 because we can cancel this with and make that a 3. So we got something non-zero in the denominator and something that limits to 0 in the numerator, which is just 0. All parabolic paths also go to 0. Okay, at this point, I'm starting to feel like, maybe we can show this one exists. So what is a technique to show something exists in here? We don't really prove anything in here, okay? Don't put words in my mouth, but we can show a pretty good plausibility argument if we switch to polar coordinates. So how would you think about, what would the limit xy goes to 0, 0 look like in polar coordinates? It translates into, how about just the radius going to 0, right? So if we could show that the radius goes to 0, if we could show that the limit is unambiguous and its radius goes to 0, if there's no arbitrary theta dependence, then it'll follow the limit exists. Now, on the other hand, if we try to change to polar coordinates and we have some kind of manifest theta dependence, that will then tell us which paths we could have used to discover the two paths which disagree. And sometimes you do need to weirder stuff, like look at a spiral path, and you'll get a different value for a spiral than something else. So here we're going to put x equals to our cosine theta. We're going to put y equals to our sine theta. And what happens to my I hope I haven't picked an example which is too hard for class today. I'm starting to worry. X squared y cubed. Can we this x to the fourth, y to the fourth. So what do we got here? we've got cosine, we've got, we have r to the 5th, right? Upstairs. And we've got a cosine cubed theta sine squared theta plus cosine squared theta sine cubed theta divided by r to the 4th times cosine to the 4th theta plus sine to the 4th theta. Now this is wonderful. The reason this is wonderful is because what we have then is that, let me call this thing f. We have that f is equal to r times this thing, cosine cubed theta sine squared theta plus cosine squared. I guess I could have factored a cosine squared. Anyway, I'm just writing it out. Sorry, guys. I'm just rewriting it. I want to draw your attention, though, to the fact that the denominator here is the sum of cosine to the 4th and sine to the 4th. Fun fact, cosine and sine, all right, they're never simultaneously 0. There is no value for theta which sine and cosine are simultaneously 0. So that means that cosine to the 4th plus sine to the 4th is never 0. So no matter what theta you pick, the denominator does not go to 0. It does not diverge. So I don't really care what happens to the numerator. It's just some value, whatever. In the limit, as we consider r going to 0, what happens? We get r going to 0, and we get something that's, I don't care what it is, it's finite. Because it's some finite number divided by something which isn't 0. Consequently, the limit is 0. Thus, the limit of xy going to 0, 0 of fxy equal to 0. For the reasons I just said but didn't write down, okay? I would like you to write those sentences if there was such a problem. Yeah? Or a sentence at least. Anyway, if you write that calculation and then you say, hey, cosine to the 4th plus sine to the 4th is not equal to 0, then we're good. Hey, what would have happened if we go back to this example? What happens if we try polar coordinates on this one? It's instructive. What happens if you try polar coordinates on this? Tripolar coordinates. Limit is r goes to 0 of what? R cosine theta over r sine theta. Oh, r cosine theta, right? Let's see how it would have gone differently. Plus r sine theta. R's cancel, right? Limit as r goes to 0 of cosine theta over cosine theta plus sine theta. Well, good news. The denominator, oh, well, is cosine plus sine 0 sometimes?
Yes.
Yeah, it is. So for those theta, the denominator diverges, right? Anyway, that has no r dependence, right? So you can just basically erase that. And you get that it should be equal to this. But it's easy to see that if you choose different theta, that gives you different values. In fact, this was nothing more than the theta equal to what? This one? That's theta what? Theta equal to 0 path. And this guy is theta equals to pi over 2, which now you can understand pi over 2, cosine pi over 2 plus, so you get 0 over 0 plus 1. That's this one. And this one was the cosine equal to 0, it's theta equal to 0, which give me 1 over 1 plus 0, which limits, of course, to 1. I mean, after you see an example like this, and the limitations of sorting through this, endless sea of possible linear and quadratic paths, you might wonder, why do we teach that at all? Why don't we just teach polars? Because polar actually has hope of calculating. I don't know. It's a question you could ask. So in terms of how you can actually calculate it, pretty much just change to polar coordinates. Again, the other thing that's possible is like a squeeze theorem sort of thing. Here's a squeeze theorem 1. If I was to ask you the limit of x, y, z going to 0, 0, 0 of, sine of x squared plus y squared plus z squared over, I don't know, x squared plus y squared plus z squared. Is that what I want? Sorry, inverse. X squared plus y squared plus z squared. Like that. So the trouble with this is that that goes to 0 as you approach the origin. So like this function oscillates like lots and lots and lots of oscillations. As this goes to 0, sine goes to infinity, goes through infinity many cycles. At the same time, that goes to 0, right? So squeeze theorem, what you do is you go, well, no problem. Minus 1 is less than the sine of 1 over x squared plus y squared plus z squared is less than or equal to 1. That's just, this is for x, y, z what? Not equal to the limit point. As long as you're not at the limit point, the sum of the squares is not 0, so the sine of 1 over that is defined. Whatever it is, it's between minus 1 and 1 because it's sine. But then multiply this by that, and you get minus x squared plus y squared plus z squared less than or equal to x squared plus y squared plus z squared. Sine of the reciprocal square, right? But what happens to the, these guys do what? As you approach the origin, this goes to 0, this goes to 0, consequently, this also goes to 0 by the squeeze theorem. We still have a squeeze theorem for multivariate limits. It's sometimes useful. Or, if you want to, we could call this g, and we could say the limit as x, y, z goes to 0 of g, well, that's really the limit as the spherical radius, rho, goes to 0 of what? Of rho squared times the sine of 1 over rho squared. Oh, but it's still squeeze theorem. Never mind. I had hoped for L'Hopital's, but my hope was misplaced. I have a few more examples in the notes. So like these pictures foolishly attempt to show you the kind of phenomena we just calculated. Namely that for this one, if you approach it's hard to see, but if you approach the origin through linear paths, the traces on the graph, they all go through the origin somehow. They all conspire to go through the origin. So if you look at any possible linear path, the limit's 0, approaching the origin of the function, in this case, that I have, where did that stupid function gone to? It is a little less complicated than what we just worked out. This function. 2x squared y over x to the 4th plus y squared. This thing, you feed it any linear path, they all work out to 0. And I have shown sort of graphically why that is down here, up to the limits of my capture of this. And then on the other hand, if you feed it this one, if you feed it quadratic paths, it so happens that the quadratic paths reveal 2k over 1 plus k squared. So you could choose different values of k to get two paths which disagree, thus showing the limit doesn't exist. And you can actually see that if you look at the graphs of this thing. That's what's next here. These are pictures of that same graph, and these are the trace of parabolic paths that go through the graph. Like this is one parabolic path, that's a different parabolic path. As you can see, this one goes to like a negative value, that one goes to a positive value. So they don't all disagree. They don't all agree. the linear paths somehow conspire to go through that limiting point at the same, through the same point. But there's some kind of discontinuity in the graph at the limit point. But it's subtle. I foolishly tried to visualize this for you guys. Oh, exciting. Let's see here. Gotta know what's on TV tonight. Oh, I know what's on TV. The Olympics. I'm just still so broken up about that snowboarder guy dragging the flag in the ground. It's really got me torn up inside that he did that. People are idiots. I'm sorry. Whee! So down here, we have now gotten to this part of the zoo. We'll get there. Here it is. These are different linear. Actually, this is one where the linear paths actually disagree, which is not the one I was just talking about. This one here, these are different linear paths. When you look at their trace, what they go to on the graph, they give you these paths. So it's a linear path in the domain, which maps up to this curved path on the graph. And those different curved paths all still conspire to go through that same point on the graph, which gives you the appearance that all the limits are equal. All the linear path limits agree and they're 0. But that doesn't say that the function's actually continuous there. It's actually got some kind of discontinuity, which you can see when you look at the quadratic paths. And here's the quadratic paths. Like, the quadratic paths are animating up and down. So as you can see, as it goes up, as it goes through that limiting point, it's going negative here, where it's going positive up there. It's hard to see, but there's some kind of like rip in the graph at that limiting point, which is speaking to the fact there's a discontinuity. You really need to like just put this thing in Mathematica and play with it for a while to really, really understand what the shape is. It's hard for me to, we're not there yet. All in good time. Anyway, so tomorrow I will go on to differentiation. That's pretty much all I got to tell you guys about limits. Either take two paths, show they don't agree, or change to coordinates. Now, if you guys got more questions about it, we can talk more about it. I'll probably ask some, I'll try to ask some ones up on the board here tomorrow for you guys to work, but not too many, just a couple. Oh, you can turn it off. I'll give you guys a test back.